Welcome to ST 118 Statistics and Applications Session 4, Part 3. In this session, we're going to focus on the common structure that governs or drives the entire process of hypothesis test. Any hypothesis test in statistics will have to involve all these components or all these aspects that we're going to talk about. Another way to put it, to make it meaningful for you or productive for you, is that this video you learn once and you can use many times. I always like this kind of formula, lesson, or algorithm or recipe because you learn one time and you can solve many kinds of problems. You can use it to handle many classes of exercises, problems, decision making, planning, and so on. So that's very useful wisdom or knowledge here. And so let's get started. So today's topic is really about hypothesis test. Hypothesis test, the common structure, common components that are used across all hypothesis tests. Okay, so we're not going to focus on any one particular hypothesis test, but we are going to talk about the juicy part, which is any hypothesis test must involve these thinking, these aspects. And very quickly, we're going to, list out the main things, which is A, you want to talk about the claim. Okay. Then B, we want to talk about the assumption of H naught. Now, of course, some of these terms I haven't really explained or talked about them, so just bear with me. In part C, we'll talk about the steps in calculations. Okay. All hypothesis tests will involve these steps, and there are 4 parts to it. And D, we want to talk about deciding, right? So deciding if we should reject H naught. We talk about H naught all the time, right? And E is our conclusion. Not our video lessons conclusion, but the conclusion template that we can use across. Okay, maybe this is the surprising part for some of you who have learned hypothesis tests before. Across all hypothesis tests, you can actually have a standardized template. You don't have to memorize. For one population, means test, you have to remember this. If it is a one population variance test, you have to remember that. You don't have to memorize this. It's supposed to be a language of communication, and so the sense of structure should be quite strong, right? That means there's less room for flexibility, which is a good thing because you just need to, in a way, fill in the blanks, right? And you don't have too much creativity because it's all driven by the data, the behavior of the data, and the governing statistics, theory or distributions. Okay, let's get started, right? So first of all, recall that our goal, what is our goal in performing hypothesis test, right, is to find mu, right? Find mu, find variance, find other aspects of population parameters. It's all about population. That means parameter can be any aspect of the population itself. Remember what's population? Population is the set, the group, the collection of all the numbers originating from the measurements. So if you're thinking about concrete things, it could be the height of individual person in the country, right? So then the so-called the statistical population is the collection of heights, sometimes repeated, if you round to 2 decimal place of a meter unit, right? Is the collection of all the numbers that represent height for individuals in the country. So the goal is to determine mu, and we talked about it a lot. So there are two ways statistically to determine mu. One is through confidence interval that was discussed in our previous video. And the other way is to perform hypothesis test, which is what we're going to talk about in general terms, not about any particular hypothesis test. But all hypothesis tests will follow this or will use some of these assumptions and steps and templates. So the goal, if we just talk about finding mu, we need to perform sampling, just like confidence interval. We must gather data. That's the only way to touch reality, to connect our statistical theory with practice, with reality. So we make measurements and we gather samples. So recall again, right? So recall that we are interested in really determining X here, the population. Right, so this is the population parameter. Population is the X here. And the population itself may have very uneven, right, kind of characteristics. Asymmetrical, roughly symmetrical, right, but not exactly symmetrical. And the shape is hardly describable by any nice, well-behaving mathematical function and so on. So the shape is a bit odd, right? That's why we have to do measurements, because we don't know, right? We don't know. It is not necessarily a sine wave, not an exponential curve, nothing that we know of. So we have to do measurements, right? So we are really interested in the mu here and the standard deviation sigma. So for now, let's just focus on mu. So we are interested in finding mu, but we are unable to find mu, right? Because X is a population of 5 million people. X is a population of 1 billion, numbers, and so on. So it's just impossible to spend that kind of budget, manpower, and technology to do that. So what we do is we perform sampling. So this is just recollection, trying to gather your thoughts about what we have covered. And through a sample size n, we are able to perform n measurements, right? And we summarize that into one point, x bar. And we summarize these n measurements into several numbers like x bar and s, the sample standard deviation, right? But that x bar is to be put on the x bar axis. And suppose n is large, then we will end up getting more or less a very smooth normal distribution, where the population mean is mu x bar, but it's proven to be mu, where the standard deviation is supposed to be sigma of x bar, but is proven to be sigma over square root n. And that's why there's a connection to n. The larger the n, the squeezier, the more protruding this x bar curve is. X bar is our fabrication. So it can be anything. It can be normal, it can be smooth. If we work harder, if we have n being very large, then it will be very smooth normal distribution, even though the parent distribution is not normal. right? So central limit theorem allows that. So we need to talk about this because, again, hypothesis test heavily involves the use of the sampling distribution of sample mean x bar in order to determine whether mu is within certain range. All right. So the difference is that for confidence interval, we produce a range to try to capture mu, or we think we are capturing mu with certain confidence. So we produce a result, we produce a guess, a range estimate, so to speak. The official term is confidence interval. In hypothesis test, we don't come up with a range. We come up with a, if I may just use the word, categorization of mu. That mu is at least 10 and above. That's the conclusion. Or mu cannot be larger than 10. That's all. Right? At first, we don't know mu. We have no idea what the number is. And after hypothesis test, we come up with a conclusion that mu cannot be larger than 10 based on the data. So that's the outcome. We don't have a specific range. We don't have a number for mu. All we can conclude at the end of a hypothesis test is a categorization of mu. Right? So the output of hypothesis test is mu greater than a particular number that we guess? Okay. Is mu less than a particular number that we guess? Or is mu statistically equal to a particular number that we guess? That's all. Right? So hypothesis test is like a categorization exercise. So let's just put it there. Similar to categorizing mu into range intervals. Governed by an inequality. Or for that matter, the inequality can be equal sign. Okay. So the idea is that why do we need this kind of output when it's not a number, right? Remember why we need to find mu? Of course, in statistical theory, we just say find mu, come up with a conclusion, that's all. But in real life, the connection is that the need to find mu often arises from the need to judge, right, who is right or wrong. The need to determine who wins, who loses. The need to, make decisions, turn left or turn right. The need to decide, right? Make assessment, plan. Should we go ahead or not go ahead? Is the satisfaction level high or low? Did we get a pass or fail? In our event organization and so on. So in many ways, performance assessments, judgment, decision making, confrontational debate and arguments, of course, legal challenges, right? We often need to know who is right or wrong, who wins, who loses, right? Like in court, right? Who wins the legal battle, who didn't. And don't be surprised that even in legal systems, it is based on probability and statistical likelihood, right? So that's where hypothesis test comes in much more favorably than just coming up with a range interval where we don't really have a conclusion who is right or wrong. We just have, this is my guess of mu. So you go and figure out yourself. So hypothesis test comes up with a yes or no, right? Or more specifically, reject or do not reject. That's where we talk about here. Reject H naught or not reject H naught. Now you begin to see, right? H naught is going to be a statement. I am right, that kind of meaning. I am right versus I am not right. So if we reject H naught, we reject the statement I am right. So conclusion is I am not right. So, or H naught says the accused is guilty of this crime, right? Or based on normal legal system is not guilty until proven otherwise, right? So H naught is The accused is not guilty of the accused crime. H0 is not guilty. H1, the alternative, is guilty. All right, now let's gather the evidence and we see if the statistics, right, leads us to conclude that we should reject H0. Therefore, concluding that the alternative, which is guilty of the crime, is going to be the conclusion. And so if statistical evidence support this conclusion, then all the more, well, it doesn't mean one-to-one, the judge still can exercise other considerations like, oh, this is a juvenile or this is whatever, right? Oh, this person was actually blind. How could you, right? Even though he might have committed this crime, he might have stolen it. It seems like he has stolen it, but it was just an accidental gesture that caused the thing to drop into, unfortunately, his bag, right? So that he's caught stealing. So the judge can still exercise other considerations that are not so translatable to numbers and statistics, right? To decide more in a more humane manner the overall context of things, whether the person is guilty or not. But statistical evidence says person is guilty. Yeah? Now, for then normal 90% of the normal cases, this will be very strong evidence, isn't it? Yeah. So that's why we have a lot of use of this. And of course, I haven't even started talking about many scientific researchers, right? Medical researchers, whether scientific means it can be physical science, it can be medicine science, it can also be businesses, financial behavior. Is it true that Black Friday, Black Monday, right? Something like that, right? End of year, stock market tends to crash. Okay, that might be a guess. Maybe it's true. It's just that we don't know the reasons. Can you see that? Yeah. So we're talking about phenomenon. We're measuring the outcomes versus our assertion. So we just do that. We're not playing scientists here. We're not scientists here. We're doing statistics here. So that's something to be clear. Right. Scientists make use of statistics, not the other way around. Judges, legal systems make use of statistics to determine criminality, not the other way around. Statistics doesn't make use of legal system, otherwise it'd be problematic, right? So statistics is at the core level. Further down, statistics will be touching reality, measurement itself, measurement science. That's a different story. Okay, so we gather the data, right? We measure n times, we touch reality n times, we interpret that measurement in sampling distribution of sample mean. So we have done that. We have discussed at length about how to interpret the sample values using this tool called the sampling distribution of sample mean. What we're going to talk about here is to make use of this tool, the sampling distribution, to further our thoughts on hypothesis testing. Okay, so let's dive in. Right. First thing first is about the claim itself. So we always start with a hypothesize claim or hypothesis claim. So this claim, right, is a claim, is a statement about mu. Okay, we have to convert any adjectives or any human oral verbal language into some sort of a quantitative measure for hypothesis testing to work. And it has to be continuous quantitative measure. Discrete or qualitative values don't work here as far as I know at all, right? Okay, so it doesn't quite work very well. So we have to claim. What is a claim? Claim in real life occurs as an argument. That's why I bring up this legal issues, right? The legal issue means there's disagreement over a particular position or claim. So the 60% of the property value belongs to me, right? So someone claims that. No, 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 no. Or someone claims 100% of this property value belongs to me. And of course, the opposing party says, no, 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 no. So there's a disagreement over a statement. Okay, so that claim has to be converted into a statement about a population mean. If it cannot be converted to a population mean, then we cannot proceed. Okay, so we have to quantize or digitize the claim. Okay, so what can be an example is, let's give an example, right? So an example could be that the claim is that mu is very low. Okay, so someone says, or maybe your friendly colleague says, "Hey, you know what? This Mamba or this Zumba mobile operator is offering a new mobile plan that is very cheap, right? How cheap? Oh, no more than $10 per month on average. I haven't been paying more than $10 per month, something like that. Okay, so average. So the claim is average monthly mobile bill is low. So that starts as a assertion without proof. That's a claim, right? Assertion without proof. Hey, you know what? This Mamba mobile operator, it's new. I haven't heard of them. Oh, well, you know what? It's excellent. I've been using it. It's the monthly bill is very low, right? Very low is what we say, but you have to quantify it in order to go through the hypothesis test regime. So, oh, it's very low. All right. So, in other words, the average, right, monthly mobile payment is low. How low is low? Let's say $10 and below is low. So we throw in a hypothesized mean. So this is this number is called the hypothesized mean, and it's different from mu. What is mu? Mu is the population average of monthly mobile bill payment, including the past and into the future. Because in order for your claim to be true, so that if you're right, if the colleague is right, it will urge us, your colleague's colleague is ourselves, right, to want to switch to this Mamba operator, right? And this better be true into the future as well, so that we can take action and it's meaningful for us to take action. Right? So the population of all monthly bill in the past and into the future that hasn't even occurred yet, but doesn't matter because statistics is not about seeing things then talk about that, right? Statistics is also about, it's just talking about the population of everything, including those that hasn't happened yet. That's possible. That's definitely very acceptable. Time doesn't exist in statistical measurement. If we define population as the monthly bill, then that will include present, future monthly mobile payments under this operator Mamba or whatever it is being called, right? So now you can see that we started off talking about this. We make a quantification of how low is low. Okay, below 10. But your colleague who says this is just claiming, maybe this colleague hasn't been having good credibility, so you kind of doubt, right? Maybe this colleague hasn't really been paying the bill himself, right? The family members have been paying and just told him, it's quite low, so don't worry about it. So that's why he thought it's low, right? So it may not be true. It's just an assertion without proof, without data to back up. So then we need to perform hypothesis test to decide whether this claim, right, is true or not true. Okay, another example, we might hear statements like, The average temperature or temperature is high. High. Or the weather has been hot. Statements like that, very, very vague. Sounds very nice and friendly, but it's very vague. Then you might say, okay, weather is hot. One way to proxy measure hotness is temperature. Okay, so average temperature is high. That's the description, right? But how high is high? Well, we can then make a judgment call and say, well, the daily temperature on average exceeds 35 degrees Celsius. So we are converting, or we are quantizing this high into a number. So again, a hypothesized mean. So these are what we say. We have the liberty. I won't say the authority, but then you can choose. Okay, you can choose to say high means this. Now, if you choose a nonsensical number, okay, like high, right? Temperature is high, so greater equal to 100 degrees. Now, of course, you can go through the whole hypothesis test and you'll find that it will reject or not reject sensibly as well. That means if you make this so high, like 100 degrees, which is boiling boiling water, right? How can that be the case? Not on Earth, I think. Then it won't ever happen, and so you are unable to make that happen. So your data will not support this claim. Okay, so no matter what, this is the first step. And what is the revelation? The revelation is that the rule. So the rule is, before I go to the rule, another third way of asserting a claim is that the average, or rather the petrol consumption for this particular car, right, is 100 liters per week. Based on, let's say, some assumptions like the normal usage, going from home to office, office to home for 1 week. Okay, so this is a very plain statement. How's the mileage for this car? Oh, the consumption for this car is 100 liters. It's a very plain statement. It's not saying it's good or bad, right? It's not saying it's fuel efficient or not. It's just saying this. So this kind of statement is also very commonplace, especially if you ask professionals like accountants and lawyers and doctors, right? So, this medicine is going to help reduce your fever in about 2 days on average. Whether it's good or bad, a fast relief or not, it's not saying that. It's just giving you a number. Right? Okay, so then this claim, which is your own observation, maybe you have been taking notes and all that, but in a very casual manner. So it's like sometimes you take down the mileage and then you can deduce it's 100 liters per week. And sometimes you forgot, right? So not very accurately. So it's a statement without proof. Then we will say that the population mean liters per week for this car. So there's only one car, there's not infinitely many car, but we can imagine there are infinitely many weeks, right? And the average of all the sometimes high, sometimes low petrol consumption for that weeks in the past and into the future averages to 100 liters per week. That's the claim, right? The claim hasn't been proven to be true or not true yet. And we are also not on the track to prove whether this is true or not true. So to use the word prove is very strong. Then we are playing scientists. We are not playing scientists here. Remember that. Huh? Scientists use statistics to help them prove certain scientific claims, to help them prove or disprove certain business laws, right? That means behaviors that govern certain performances. Okay, so like economic crashes, what factors are strongly lead indicators to economic crashes, things like that. So So that's the kind of scientific use, right? Very systematic use of statistics to prove certain concepts, laws, assumptions, right, and theorems. But this claim here is just an assertion without proof. Okay. So the rule that governs this is the meat of it. Here's the rule that you should remember. Right? The rule is the claim statement. I will just abbreviate as claim. Huh? So the claim always goes to H naught, right? Except for equality claim. That's it. So very, very important rule here so that you can always get your exam questions, test questions right the first time, right? And one time only. You don't need to repeat. You don't need to be unsure. Okay, so in other words, this rule says situation number one goes to the claim always goes to, sorry, I wrote wrongly. Almost inverted the whole thing. Okay, so the claim always goes to H1. Okay, claim always goes to the what we call the alternative hypothesis, H1. And therefore we can write down H naught because H naught covers the other complementary interval. So going from minus infinity to infinity, the whole stretch of horizontal x-axis, if we say that if the claim is mu is less than 10, right? So marker is at 10, anything less than 10, that's the claim, right? So the claim statement, this statement, goes to H1. So let's write this down. Okay, so what we have is, so in example 1, the claimed statement goes to H1. So we write down H1 mu less than 10. Okay, so then what do we write for H naught? Because 10 and below has been occupied by H1, so 10 and above, including 10, has to be covered by H naught. That's it. So that as a pair together, they cover the entire interval from minus infinity to infinity. Okay, is that all right? So claim always goes to H1. Number 2, claim is mu greater equal to 35. Okay, so the claim always goes to H1 except for equality claim. Is this an equality claim? No. Number 3 is equality claim, pure equal sign. The claim statement includes only pure equal sign. This statement does have the equal sign, but essentially it's an inequality. Okay, so just to be clear what I mean by equality claim. Yeah, this is where many students, even those from A levels and poly students who have done intro or even advanced statistics, end up kind of making the mistake of, oh, so long as there is an equal sign appearing. That's not what I'm saying here. But their understanding is, so long as there's an equal sign appearing, then this statement goes to H naught. That's wrong. Okay, that's wrong. Okay, so this is an inequality claim, essentially. For a continuous variable, right, like mu is a continuous real number, a number on the real axis. It's whether you include the 35, the dot on the 35 or not, is not really very material. Okay, so that's why this is essentially a claim that is not an equality claim. So it goes to H1. So we write down H1, mu is greater than 35. But as a convention, we move the equal sign, the sign itself, to H naught. Due to our next rule, okay, so due to statistical convention, we always move the equal sign to H naught. Okay, so this is the way we write for this kind. And likewise for a claim that involves less than or equal to. So average monthly bill is low, but we can translate it to average monthly bill is less than $10 per month, right? But it doesn't make a difference if we say average monthly bill is less than or equal to $10 per month. It doesn't suddenly move it from H1 to H naught. It should still stay at H1, right now, yeah? So that's why that's the common confusion I notice, especially for students who have learned intro stats before. Don't know how they learn or where they learn from, but somehow it's just their misunderstanding, right? So long as they see an equal sign, then that whole statement goes to H naught. That is not correct. Huh? So follow this, which is simple, and simplicity usually is the right way to go. And lastly, we look at this one. So we say, okay, claim, this is a claim. Mu equals 100 is a claim. It goes to H1, right? Wait, but does it satisfy the exception criteria? Yes. Yes, it does. So for number 3, right, we will put the claim as an exception in H naught. Right, so H1 becomes mu is not equal to 100. So that's the way we determine, all right, we determine how to place the statement, the claim statement in H0 and H1. And this is super important because if your thinking is there are only two spots, either put the claim statement in H0 or H1. If your thinking is like that, let me give you a new perspective. There's 50% chance of making a mistake if you're not aware of where exactly to park the claim statement. And 50% is a lot, not 2%, not 5%, it's 50%, right? Half the time you'll be wrong if you're not clear about this rule. Okay, so I like this rule because it's very simple and it takes care of all circumstances, right? So try to use this. Okay, so now every hypothesis you test, you have to kind of quantize or digitize the claim, make it a statement so that it's very crystal clear, right? So it's like, what do you mean by low? Oh, $10. Okay, then what you're saying is mu is less than 10, is that right? What is mu? Oh, mu is the month population mean of all monthly mobile bill that is subscribed under Mamba operator. Okay, fine. Yes, correct. So now this is a crystal clear representation of the claim that is initially a bit fuzzy, right? So now we place the statement correctly in H1, and then we perform other steps. Okay, what are other steps? We're not going to go through every single step, but generally, what is the next item to think about? And that is assumption of H naught. Assumption of H naught means we assume it is true. Remember what's H naught? H naught is the statement about me. The H naught is the statement that mu is greater than or equal to 10, mu is less than or equal to 35, mu is equal to 100. Notice that the equal sign is always attached to H naught. That's why we have this exception. Okay, this is a convention, not invented by me, but agreed upon by all statisticians in the world from the past and into the future, including yourself in the next generation. We could have observed another convention by swapping them, equal sign always attached to H1 and all that, but let's not do that because it's very confusing. All statistics literature will, write this way, put the equal sign in H naught. Some literature, probably the older versions of textbooks and all that, might even put mu equal to 35, mu greater than 35. Okay, so the actual meaning is still this, that mu is less than or equal to 35, mu is greater than 35. Okay, so they might write in terms of the symbol, write as equal here. The reason is we are going to assume, okay, we will assume that hypothesis test is throughout the hypothesis test. I'm going to write HT, all right? Just HT to represent hypothesis test. Throughout the hypothesis test, oops, moving the wrong stuff. Okay, so throughout the hypothesis test, we assume that H naught is true. Until when? Until data reject H naught in favor of H1. I put in bracket because when you reject H naught, what is left is only H1. So certainly, right? Some textbooks will say data supports H1, but let's standardize it to always refer to H naught because we are always assuming H naught is true. That's the basis we are operating on. And you'll see why that's important in a while. Just let me finish up without writing the wrong sentence. At a significance level of alpha. That's something in the calculation step that I will be talking about. So at the stated significance level. So I'll talk about what is alpha in a while. But the important thing is throughout the hypothesis test, and we have several steps, right? Just now we have part C, calculation steps. Not many, but 4 or 5 steps, 3 4 steps. We throughout from the writing of the hypothesis statements to the conclusion, it's all about assuming H naught is true. Until data comes in, we perform calculations, then we decide whether to reject H naught or not, right? And once we reject H naught, then we are going to conclude that H1 is, not rejected. We're just stating plainly, stating as a matter of fact that H1 is not rejected. That's all. We're not going to say H1 is correct. Hence, we have proven beyond reasonable doubt that H1 is correct. H1 has been shown to be right. We're not going to say right or wrong. We're not going to say true or false, although we describe them here. Right. Our statistical conclusion is going to be very mechanical, right? Very robotic in some sense, driven solely by data. That's the beauty of it. That's why this hypothesis test steps, they are being followed throughout the world because it's like what we say that data doesn't lie, right? It's a cold-blooded data. If it is high, then it is indicative that the assumption that mu is high is likely to be true. And if it's low, then otherwise. So first, we got to make some assumption. And the usual mathematical trick is, let's assume that this statement is true. Now, you might be wondering, isn't that dangerous? If we assume that it's true, then wouldn't that assumption itself make data to become more in favor of H naught, right? That to make it true. That means the assumption that is true makes itself true. No, don't worry about it because these two parts are clearly separated in the steps. Very clear cut, right? So the way we wrote down the statement has never touched data. The way we positioned the H naught statement and we wrote down the claim did not involve data. In fact, we don't even know the data yet. The data hasn't even been measured yet. It can be measured already, but we haven't processed it, or it doesn't even have to be measured even at all. So we don't even know the data. So that this positioning of the H naught statement is totally independent of what the data will tell us, right? So there's no sort of recursive influences, right? That the mere assumption of H naught is right is going to make H naught even more right. and change the data, right? So it's not going to be happening. So no worries about that. Okay. So, but this is important. Why? Because when we assume H naught is true, mathematically we can proceed, right, with any occurrences of mu in the formula, in the distributions, in whatever calculations. Whenever there's a mu occurring, right? For example, calculating the z value. So the z value of x bar is x bar minus mu divided by sigma. We need a mu. What is our mu? When the mu can be 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, because we don't know mu, correct? So what number are we going to substitute into that formula? If we cannot have a fixed number, then we forever cannot conclude, right? So to untie or unlock that loop of indefiniteness, we assume first, right, without invalidating the final result, we assume H naught is true. The usual trick mathematically is that if you assume this statement is true and you just go towards its logical conclusion. So if it's assuming something weird, sure, let the something weird be assumed. Then it will lead to something even more bizarre. And finally, the bizarre conclusion will not match what you observe in the data because the data is not bizarre. Now, something towards that extent. So at that point in time, we're going to say that, hey, this bizarre H naught doesn't work, so we have to reject it. Now, that's the logic behind. However, on the other hand, if the assumption of H naught is benign, it's like, okay, H naught is, or Mamba operator, right, is charging bills that are sometimes $9.50, occasionally $12, right? But your colleague just rules that out and say, but other times I pay only $9, right? So he thought average must be less than 10. When actually you get the sample data, $9.50, $12, then $9.80, $9.70. But the single $12 kind of averages up the monthly bill to $10.70 maybe, right? So then it's going to burst, right? So it's a reasonable H naught. So it is actually not wrong. And finally, if your data is not small enough to pull the test statistic, we're going to talk about that, to conclude or to reject H naught, right? So we don't have evidence to reject H naught, then we have to stick with it. And the assumption that H naught is true, right? It fails to be rejected by the data when we assume it is right. Then it has to be true. It's like saying that the legal system says that the accused is assumed innocent until proven otherwise. Okay, so if you don't have evidence, if the lawyer doesn't have evidence, if the lawyer doesn't have witnesses, if the lawyer doesn't have this, doesn't have that, there's no data, so to speak, right? For anyone, definitely for the judge, to conclude that there's evidence to reject the idea that the accused is guilty. Then the accused is not guilty by assumption that it is true in the beginning, right? So that's the logic behind. So in other words, we are following the legal system that H naught is innocent until proven otherwise. So that is the logic behind. Okay, so this is important to keep in mind so that whenever we see mu, we have a fixed number. What number? The hypothesized mean number to plug into the formula that contains the value mu, because we don't know what the value is and we don't know whether it's greater equal to 10 or less than 10, right? So we just put 10 in. Why? Because that is the hypothesized mean. Now, if we choose this to be an absurd value, 100, let's say, right? When actually all the mobile operators are charging $10 and most $20. Where is this claim about $100, isn't it? So you put something absurd, of course it will be rejected quickly because your data is going to average around $11, $10.50, right? It's way below $100. So how can it be greater equal to $100? So it will be thrown out. right away. It's like such an obvious case relative to the whole hypothesis test sequence. Yeah. So you can put any number you want, but you're just wasting time because the answer will still be consistent. So most of the heated debate, strong arguments, unresolved disagreements involve this number being somewhere in the middle. Right? This number is translated in such a way that it's somewhere in the middle, and we cannot agree. Right? The two parties, the two disagreement parties, cannot agree to whether the population mean is actually below or above. That's the main driver of many of those arguments. Okay, so quick example, right? Example is that example 1, right? So H naught says mu is greater or equal to 10. So in particular, mu is equal to 10. This is obvious here in the third part, the equality claim, right? But then in these two parts, what do? We observe that the equal sign is there. You see now why, as a convention, we always shift the equal sign to H naught, so that whenever we need mu, we can legitimately use that equal value to make mu calculatable. It's a number, right? It's 35, not a range of numbers, which is typically hard for whether for computer to calculate or for mathematical derivation to be carried out. Okay, so whenever we need a value for mu, right? We just use the hypothesized mean, which is 10. Because we assume mu is equal to mu 0, which is 10. So we can just proceed with the calculation. Okay, so that's for part B. And these are general rules, right? Because it doesn't apply to just one hypothesis test. It applies to 2 population means tests, 3 population means tests, median tests, normality tests, equivariance tests, all tests. Throughout, whenever you have written down correctly the H0 and H1, we will assume H0 is true. Whatever is in H0. That's why it's very useful to know this, not just this statement alone, this B statement alone, but the fact that it applies to all hypothesis tests is a very, I hope, relieving thought. Yeah, very, very liberating idea that you can just make this assumption, understand this assumption in all hypothesis tests, so that even if the hypothesis test is very complicated and hard to understand in certain calculation parts, this part still remains, right? In fact, all the parts that we talk about still remain. Okay, next we want to talk about part C, the calculation steps. So C, right, we want to talk about C part 1. C part 1 is to select significance value. The significance value. So just like confidence interval, where we will select a confidence level, well, as a student, you will read about the confidence level in the exercise or the exam question. And likewise here, right? As a student, you will receive this information from the exercise or the exam question. So select alpha. Again, what I observe as a common mistake or misunderstanding, let's say, among students is that alpha plus confidence level is 100%. That's not true. Okay, you can have a 90% confidence level and a 5% alpha, so they don't add up. And that's fine. You can have a 99% confidence interval level and 10% alpha. You can have multiple confidence interval, 90, 95%, 99%, and an alpha that is 2%. So this is just another selection. So what is alpha? Alpha is typical values. Typical values will be 10%, okay, 5%, sometimes 2%, but will go to 1%, sometimes 0.5%. But that's about it. Okay, so you have a choice and you don't have a choice, right? So you do have a choice amongst these reasonable values, right? Typical values for alpha. And basically what that means is that it's trying to indicate the degree of impossibility. All right, what kind of probability of occurrence is considered rare, considered unlikely to happen. Okay, so that's our significance level. That means when it does happen, wow, this is significant. So layman's way, right? Most of us might think that if it's more than 50%, maybe that's considered rare. Okay, we won't use the word rare, but we call it more likely to happen. But we want it to be rare. Rare as in very unlikely that this would happen, this event, this occurrence will be observed. Very unlikely. What is unlikely? We got to convert it, and that's basically the meaning of significance level. All right. So the way we can think about it using example 1 is that I'm going to draw a bit smaller without losing much of the features here, because it's basically a bell curve, right? And because we're playing with, or we're operating on the x bar, and with n being large enough, it will be normal distribution. So the example 1 here, right? Remember, recall that it is h1 mu less than 10. h1 is the so-called extreme end. So h1, we are always assuming h0 is true. So we are reluctant to give up h0 in that sense. So the extreme one is h1. Extreme end is h1. And h1 points to the left side. I'm kind of using this arrow, right? This less than as an arrowhead to say left side. But it works. So let's just live with that. Okay, so the alpha, example, let's just say alpha. So let's just pick alpha. Alpha is example, right? So alpha is 5%. Alpha is 5%. 5%. Alpha equals to 5%. Okay. So now what we have is that this is going to be 10, and our alpha will be on the left side. So this is alpha. Then naturally the white portion will be 95%. Okay. So this is the case when we have h naught mu is greater or equal to 10, h1 mu is less than 10. Okay. Then we can also talk about the second case, which is that our x bar, right, and then we have a simple bell curve here, and it is going to be centered at 35, right? Of course, it's helpful to see the hypothesis, which is mu is less than or equal to 35, h1 mu is greater than 35. Okay. For a one population mean hypothesis test as an example. So again, using this greater than as an arrowhead pointing to the right, we're going to say that the whole alpha is on the right tail, and so the full weight of alpha is on the right side, like this. And of course, reason why I want to go through the 3 cases is that interesting case comes in the 3rd case. Now another bell curve, right? And the center is going to be 100, where the hypothesis is mu equals to 100 and mu is not equal to 100. Okay, so at this point, it's a two-tailed test, meaning we're going to split alpha into 2 halves unbiasedly, right? My shading is definitely not proportionate because I want to make it visible, right? So my 5% here, so this, I cannot call it alpha, I will call it half alpha. So that's 2.5%. And likewise, this is another half alpha. So altogether, there are 5%. But positioned this way, right? Half. We have to do it this way because it is equally likely for the data to be way smaller than 100, so much so that it's no longer equal to 100. Or way larger than 100, like 250, right? Or 125 or 112, right? So much so that it is no longer considered to be 100 statistically. What about here in between? Well, that's the statistical noise that we can accept as random fluctuations without invalidating the conclusion that mu is equal to 100. That's the reason why we want to perform statistical tests rather than just comparing the X bar number with the hypothesized mean. So our sample mean says 92. Compared with 100, of course, it's never exactly 100. So does that mean we reject H naught? No, right? Because there's always some randomness. If you happen to gather a sample that averages X bar equals to 100 exactly, do you conclude therefore that we do not reject H naught? Can't tell. Because the very next set of sample might make, right, the test statistic. The X bar can be 110, but then the standard deviation can be small, like 1, then you might end up going into the rejection region. So that's the scenario. So one tail test is always one side, on the left side. Left tail test. Right tail test, always on the right side. Two tail test, always half alpha, one half on each side. So that is to select a significance level. Okay, and then we have C, step 2, select a distribution. Sampling distribution all right, or I should say standard sampling distribution of sample mean. So this standard, right, is dependent on what population parameter you are estimating. So for mu, right, we use Z or T, right, and I would suggest that typically use T. Okay, except when n is very large. But then even when n is very large, degree of freedom will be very large too, right? And T will approach Z anyway, so it doesn't really matter too much. Or population is normal. And sigma is known. Typically, sigma is not known. In practice, sigma we do not find out easily because if we don't know mu, right? That's why we perform this whole sequence of hypothesis test. And if we don't know mu, very likely in practice, we also don't know sigma. So this is usually only an academic exercise or a mathematical derivation where we say, okay, assuming we know sigma, then this will be what happens. Okay, so in practice, when you have a bunch of data, in data analytics, when you're supposed to analyze the measured data, collected data, sample data, we're going to just assume that x, right, x here is going to be normally distributed, roughly normally distributed, because t requires the parent distribution to be normally distributed. So for t to be the selected distribution for x bar, we need to assume that x is normally distributed, except we compensate for the lack of knowledge of sigma, so we use t. Right? So usually that's not going to be far wrong, especially when we are helped by a large n. Okay, other choices could be that other choices, right? So others, just to other distributions could be chi-square for chi-square independence test, for goodness of fit test, right? For variance, not variance equality, but variance test, as in is variance larger than 10, is variance larger than 100, that kind of test. One population variance test, so chi-square. And F test, right? For two population variance tests, are they equal or not? For ANOVA test, we will talk about it in the next video session. And various other tests regarding two variances or two squared differences, something like that. So F test, right? And of course, there are many other distributions. We will just focus on Z and in particular T for now, right? So that is, we choose one. So in other words, we also don't choose much. And why we have to say this is because it's a conscious step that we use. What are we testing? So if we are testing for mu, then we don't have much of a choice. It's either Z or T. If we use Z, then we use the Z formula for our next step, which is to calculate the test statistic. Okay, calculate the test statistic. So it is either Z equals to x bar minus mu naught over sigma over square root n, but you will have to know sigma, and typically we don't, right? Or you use t. If you use t here, you got to use t here. Then it will be x bar minus our hypothesized mean. Why? Because our mu is assumed to be true, or rather our h naught is assumed to be true, so our mu is equal to h naught. That's what I was trying to hint at, right? So now you see, we actually need mu, the population mean, but we don't know. So what's the value to substitute for mu in order to carry on with the test statistic? That's our mu naught. Over, and t would have adjusted for our lack of proper or accurate estimation of sigma. So we can use S. That's why we can use S. And then for others, we have chi-square test statistic, F test statistic, and so on and so forth. So we'll be focusing on using this. So calculate the test statistic. Okay, and then we have our next part. Once we have the test statistic, we can calculate the p-value. P-value is a very core idea because you see that being used a lot. Just Google around for, let's say, medical research papers on COVID-19 drug efficacy, or some scientific journals, right? Or some business journals, some business research journals. You'll find p-value, or sometimes they put bracket p equals to 0.00015. Now that number that p equals to is the p-value. But what is p-value, right? How to calculate it? First of all, calculation. So how to calculate p-value? So p-value is, first of all, equal to two parts, right? For one-tailed test situation, it is the area starting from test statistic, whatever test statistic you have used, right? If you have used t-distribution, then you use t-test statistic, then you use that value. If you have used z-distribution, you use the z-test statistic, then you use that value. If you have selected chi-square because you're doing variance test, then you must calculate the chi-square test statistic. Then you start from that value. So, okay, starting from the test statistic, towards the tails infinity. So if the test statistic lands here in the white area, right, then the p-value is the region starting from the test statistic, shading all the way towards the infinity, towards the tail area, like that. If it ends in the significance area already, it's still towards the infinity in the tail area. Okay, that means the sidedness of the p-value for one tail is very clear. Likewise, in the right tail case, if the test statistic lands here, then you go towards the plus infinity because the tail is in the plus side. Right? Likewise, if it ends inside the tail, you still go towards the plus infinity. In the two-tail case, right, for two tails test, you want the area starting, again, same thing, the area starting from test statistic, right, towards the nearest, nearer, because there are two infinities, right? The plus infinity and negative infinity. So the nearer infinity, right, then times 2, multiply by 2. Then multiply by 2. Okay, in other words, if our test statistic lands here in the white area, doesn't matter, on the left side of the white area or the right side. On the left side, you find the area from starting from the test statistic all the way to minus infinity, then you times 2. If it's on the plus side, then you shade the area, or you find the area starting from the test statistic, shade all the way to the plus infinity because it's the nearer infinity, then you times 2. And then it'll be correct. So that's just mechanically, right? How you calculate the p-value, okay, correctly. Now, of course, there's a reason why we times 2, yeah, because we halve the alpha, so that as a producer calculator for p-value, you want to be allowing the reader, the consumer of the p-value, to compare with alpha. So the end goal for p-value, the published p-value, is to compare with alpha, for the reader or for yourself to compare with alpha. So you don't want the half p-value to compare with half alpha whenever it's a two-tail test, right? Quite tedious. Oh, is it one tail or two tail? Oh, it's two tail. So I better half alpha to. It's just confusing. So the convenience and the ease of using p-value is that the producer, right, the calculator, the generator, you yourself maybe, will have to be careful, right? Take a bit more trouble. But the consumer, the reader of p-value, anyone reading a p-value, like the many readers of scientific journals, business research journals, right, the many readers of p-value, they just conveniently compare the p-value with alpha. And sometimes when the p-value is very, very small, like 0.00 something, right, 2 zeros something, it's already smaller than 1%. Definitely smaller than 5%. Definitely smaller than 10%. So in other words, you don't even have to worry about alpha. The publisher, the scientist is saying that our test result is so significant. Please pay attention. It's genuinely very interesting, right? Very effective or very powerful or high performance or whatnot, right? So please take note, something like that. So they just published the p-value, which is a very small number, is enough to be saying something, saying a lot, right, about what they've done. But of course, if your p-value is larger than alpha, right, then it is not significant. So it can be also published to say otherwise. Somebody claimed this. After our research, p-value is 0.35. In other words, not significant, right? So that's kind of not supporting the claim or something like that. Okay, and that is just sharing with you what is the way to calculate the p-value. So what's the meaning of p-value itself? So the meaning is this, right? Remember, we are always assuming that H naught is true throughout, including the interpretation of p-value. So what's the meaning? The meaning of p-value is that if H naught is true, right, then the probability, the chance, the probability of seeing what we have seen. I will explain in a bit. What we have seen is small, very small. I'm putting the word very to emphasize the magnitude of p-value being very small. P-value smaller than alpha. So this is what it means. Okay. But, here's the but. But we saw it. So what does that mean? Okay, so assuming H naught is true, assuming mean, population mean, where's our population mean? Assuming population mean of the bill is $10 or more, very expensive, right? Assuming it is true, and we got a p-value that is small. That means it is inside this tail. That's why it is smaller than the alpha shaded region, the green region, right? So if our p-value is small, that means our what is it? Our test statistic would have landed here, right? Would have landed here. And the p-value, definitely, the tail end of this is lesser than the green region, right? Because it covers only the tail, the green region covers not only the tail and this extra region. So p-value less than alpha. What does that mean? Alpha is the degree of rarity that we have chosen. We agreed up front. Remember, we selected it before we get the data, before we saw the data, the test statistic. So we agree that, and there's not much choice. Let's say 5%, right? So there's not much choice that anything larger than 10%, smaller than 0.5%, you start to attract frowning eyes. Why are you doing this, right? You attract suspicion, you attract reasons to discredit your conclusion. So why are you going through all this? So you don't have much of a choice. So internationally, whatever we are testing, we're just going to pick 5%. When p-value turns out to be 1%, what does that mean? You see that p-value always starts from the test statistic. In other words, it is anchored on the data. It is defined by reality. If the data is, very extreme, very into the H1 area, then we basically will find that it is a very rare event, right? If we assume H naught to be true. So if we assume the monthly bill payment is expensive, like $10 or more, then how come our test statistic is indicative of a very small p-value? The p-value means the probability of seeing what we have seen. What have we seen? We have seen we saw it. What is this it? This it here is the test statistic, right? Remember what is test statistic? Test statistic is derived from data, and p-value is derived from test statistic. So they're all connected. P-value basically is defined by data. So if the data shows us that it is what we have seen in the data has a very small chance of happening if we assume that the monthly bill is very expensive. How come we keep seeing data that shows $5, $8, $9, $5 again, you know? How can the sample bills be averaging to give such a rare event? But that event happened. Can you understand the logic here? If I assume your H0 is true, then the chance I calculate the theoretical chance of seeing what I'm seeing now, the data, is 1.2%, 0.7%. Very, very rare, right? In fact, rarer than the 5% that we have agreed upon. So what can you say? That I'm lucky? I'm super, unfortunate or what? Cannot be, because we randomly pick the bills, right? We randomly pick the monthly bills, and the usage is random. There's no proper coordination. So how can it be all the time always getting low payments when you are claiming that it is very expensive, correct or not? Yeah. So what can only happen is that we are going to reject H0. Now you understand the logic, huh? If I assume you are right, then we are seeing something weird. We are observing the impossible. Okay. The only way out is that no. What we are observing is very commonplace, but our assumption that you are right is wrong. So maybe the population mean bill should be $5. That means shift it to the left. If you shift the whole curve to the left, then you say, no wonder, right? No wonder that our test statistic is always centered in the middle. That's the reason why. So whenever p-value is lower than alpha, we will reject H0. That is going to be true all the time. Okay. Now, of course, we also have the other case. The other case is easier to fathom, to interpret. For example, we are saying that mu, the temperature is higher than 35 degrees, right? And our test statistic shows that the position is here. Okay. And therefore the p-value is towards the tails infinity, right? So towards the tails infinity, so over this side. Now clearly you can see that the area of the orange, which is the p-value, is larger than the area of the green, which is the alpha, right? So p-value greater than alpha. What does that mean? If we assume H0 to be right, if we assume that the temperature is not so high, not larger than 35 degrees on average, then the chance of seeing what we are seeing is 0.62. It doesn't have to be 0.62, it can be just 0.25, right? Just merely larger than alpha is enough to say that, of course, it's quite normal. What's the big deal about getting an average temperature of 30 degrees when, of course, the weather is not as hot as you claimed, right? So that's why we fail to reject H0. Okay, so we can put that understanding down here. I was using the red color. So I've been saying this, right, a few times, so it's good to put that down because it is also a general truth and important structure of all hypothesis tests, that if the p-value of any test, right, is less than alpha, we will always reject whatever is in H naught. Okay. And conversely, if p-value is greater than the equal is, I would be more on the safe side. So greater equal to alpha, we do not reject H naught. Okay. Now, one additional case that I want to caution you guys is that if p-value is roughly approximately in the range of alpha. Now, it can be that it is smaller, it can be that it is bigger than alpha. So, for example, alpha is 5%, p-value is 0.045, so 4.5%. Alpha is 1%, p-value is p-value is 2%, so do not reject, right? But that kind of situation, right, be careful. If you are the producer of this p-value, you want to check your answers again. You want to justify your alpha. Because if p-value is 2%, you choose 1%, H naught will not be rejected. You choose 5%, H naught will be rejected. If your promotion depends on H naught being not rejected, or the other way, it doesn't matter, right? Then you will have an incentive to pick the right alpha so as to protect your own self-interest. Can you see what I'm trying to say? Yeah. So in these cases, you want to really, if after checking your p-value is very close to alpha, then you better justify your alpha very carefully. Have a statement, have a paragraph to explain why you choose alpha to be 5%, why you choose alpha to be 1% or 10%. Yeah. So you want to say something about that because your p-value is very close. If you still cannot explain it, then you want to be, you may want to redo your experiment, right, to increase sample size. Best is to increase n and redo the experiment again. So when you increase sample size, you touch reality more. You're going to be getting more reliable p-value that doesn't hover around the alpha region. Alpha region means anywhere from 1% to 10%. Your p-value is either very, very tiny, less than 1%, or very, very large, like 20%, 30%. That's fine. That's very clear, right? So when it's around the range of 1% to 10%, be very careful. That's when you're producing the p-value. If you are the consumer of p-value, you're the reader. Some scientists, some business consultants says, we have done our survey. The p-value, p-value, you have learned, right? Okay, so they tap on your knowledge of statistics. You learn that p-value, our p-value is 0.075, so 7.5%. Again, choice of 10%, reject H naught. Choice of 5%, do not reject H naught. So now what? If rejecting H naught is in favor of the business consultant, right? Then there's conflict of interest, right? Then that's why their proposal should be accepted. That's why they win the argument. That's why and this and that. Then you want to be careful, right? Then want to be on the alert. Then you want to be challenging them. I'm sorry, why do you choose alpha to be 10%? Because if you choose 5%, then I don't see why we should give you that contract, something like that. You want to be careful. But if they say, look, after our survey of consumer satisfaction, our p-value is actually 0.005. So it's actually 0.5%. All right. Okay, fine. I mean, if you choose alpha to be 0.5, then it's indeterminate, right? But it's already on the low side, or it's just 0.1%. So the case is still strong that, yeah, it's very indicative. Or p-value is 25%. Okay, it's not like 70%, but 25% way outside the alpha region, fine. So very clear cut. So I'm just saying be alert. Okay. So that's on the usage of the p-value side. And finally, so we come to the E part, which is the finally part, the conclusion. So the template, conclusion template. In other words, all hypothesis tests will look like this. So you want to say something like this, that you want to say something like since, right? Since p-value is equal to 0. I'm just putting in some numbers. You can replace those numbers with your actual findings. 0.00015 is less than alpha, which is equal to 5%, right? So 0.05. In this case, less than means we do not, we always reject, right? So so if I underline, it means you will replace it with your, we reject. We reject H naught and conclude. So we reject H naught because p-value is less than alpha, and conclude whatever that you did not reject. So if you have rejected H naught, you want to conclude about H1, right? But you want to say that statement without using Greek. You say that statement in English. Yeah. So suppose we are talking about here, the first example, right? Then we say that and conclude using example 1. Conclude that the population mean it's always about mu. It's always about population mean monthly bill payment right? Mu is less than $10 per month, is less than $10 per month, right? So you want to write something like an English prose, more friendly form. But important thing, at alpha equals to 5% or 5% significance level. So this is the template. Okay. This template doesn't change much. In fact, it doesn't change much at all other than those values. So let's say in this case, the second case, right? P-value is large. So we say, since p-value is 0.55, it is not less than, because we want to detect if it is less than. So if it is greater or equal to, we say not less than. Write a less than, then cancel out. So it is not less than alpha equals to 5%. We do not reject H naught. Since we do not reject H naught, we're going to conclude about the H naught statement without the Greek letters. So in English and hopefully a friendly form. So we say something meaningful to the context that gives rise to this test. So if this is about temperature, then we want to relate back to temperature. This was about the monthly bill, so we relate back to the unit, that's dollars, not cents per month, but also per month, not per week. Right? So let's finish up and we say, since p-value is 0.55 is, not less than 5% alpha, we do not reject H naught and conclude that the population mean temperature or monthly temperature, right, is, we're talking about H naught, less than or equal to 35. What's the unit? Degrees, right? Degrees Celsius. So it's less than or equal to 35 degrees Celsius at 5% significance level. So this conclusion, this template, is going to connect back what is very mathematical and algorithmic, right? Calculation oriented, distribution, all that stuff, back to the storyboard, so that we talk human again. But we need to quantify this. Remember our p-value just now? Yeah. If you don't quantify this, then when p-value is very close to the alpha region, like between 1% to 10%, right? Then the choice of alpha can invalidate this. So we need to be accurate with what we say. The conclusions template is written this way. I highly encourage you to just follow this template in your statistical conclusion, so that you are always saying what is exactly right, not claiming what you haven't shown to be right. That means over concluding, or under concluding. That means you're not saying what you have already discovered. All right. So this will be the best arrangement. It's very methodical, right? You just like one thing leads to another, and you won't be wrong all the time. Okay. And finally, after this, there's a sort of a optional step, but becomes important in real life, which is to go beyond the conclusion. So secondary conclusion. The secondary conclusion part is more about good or bad, right? More about assessment, judgment. You're judging, right? Is this therefore a good thing for us? For whom? Right? Good or bad for whom? Do we have any necessary action, right? Or not? Or further plans. Therefore, we should do this because the temperature is so high. Therefore, we should do this. We should install aircon. Right. So actually, originally the business decision was: should we buy new aircon, more power efficient aircon, so that it's cooler and consumes less energy? Because recently it has been so hot, right? But is that proof that recently temperature is rising? Then we measure, we perform hypothesis tests, rejected, right? Or yes, we suppose it's rejected, then temperature is high. But we fail to reject, so no action is our action, right? Because no, temperature is not that high as you claim it to be. So conclusion is, our judgment is no action. Don't buy the new aircon. Don't install aircon. At least not yet. Right? Okay. So that is necessary because that's what started the whole process of hypothesis test and data collection in the first place. Yeah. Okay. But this conclusion template is the final part of the hypothesis test. Okay. And for humans, for business executives, the final step is to make a judgment on it. Don't hand in the conclusion template as if submitting a homework assignment, because you are not going to be dealing with homework assignments. You're going to be dealing with decision making, right? Judgment, assessment, actions. All right. Thank you very much for your attention. This concludes our discussion on the general structure and logic and assumption behind all hypothesis tests. In the next few video sessions, we're going to discuss more about those individual tests that achieve specific goals about certain population parameters. See you then. Bye.